Image diffusion models exhibit emergent temporal propagation in videos. This paper introduces the drift framework, and it really changes how we think about what's hiding inside these huge image models.
It really does. The core idea is genuinely surprising. I mean, it suggests that pre-trained static image models, think Stable Diffusion 2.1, they inherently capture these incredibly rich semantic structures.
And those structures just unexpectedly translate into reasoning about things over time in videos.
Exactly. It's an emergent capability.
They found that the model's own self-attention maps can be, well, completely reinterpreted as a temporal propagation kernel. This isn't something it was ever trained to do.
Right, but it works. It provides this really reliable pixel-level connection across frames, which lets you do zero-shot object tracking, basically right out of the box.
And that's what leads to the GIFT framework diffusion-based region inference with cross-frame attention for tracking.
And it achieves state-of-the-art results on major benchmarks, like Davis 2017. And the key thing, the really crucial part, is it does this without a single frame of video-specific training. It's all emergent.
Okay, so let's unpack that. Because the jump from making a static picture of a dog to, tracking that same dog as it runs through a video, that feels like a massive leap. How does an image model even begin to understand motion?
Well, it all comes back to the training objective. To do its job, to denoise an image, to reconstruct a coherent scene from just random noise, the model have to implicitly learn these very deep connections between all the different parts of an image.
It has to know that this patch of pixels over here is the dog's ear, and it belongs with this other patch that's its tail.
Precisely, and we've seen this before, right? Within a single image, you'll see the cross-attention for a word like cat. Might just be a rough blob over the cat.
Yeah, a very coarse localization.
But then the self-attention kicks in. It acts like a spatial label propagator. It refines that blob into a super detailed, fine-grained segmentation mask. The model is basically asking itself, how much does this nose pixel belong with this torso pixel for every single pair?
Okay, so that spatial relationship is the foundation. The real genius here seems to be how they repurpose that for time. How do you go from pixel to pixel in one frame to frame tracking?
You just compute a cross-frame attention map.
Right.
So normally in self-attention, you're comparing the query matrix of the frame, QT, with the key matrix of the same frame, QT.
Right.
To get that temporal link, you just swap one of them out. You compare the query matrix of the current frame, QT, with the key matrix of the previous frame, KT1.
And just like that, the attention map becomes a motion tracker. It's using the learned semantic features to say, okay, the object in this mask from the last frame, where did it move to in this frame?
Exactly. You're querying the new location based on the semantic identity you already established.
Yeah.
It's so compelling because it just bypasses the need for things like optical flow, which can be really error-prone, or dedicated video encoders that you have to train.
The motion cues are just already in there, baked into the model.
They're implicitly encoded.
Which brings up a really critical question, especially for anyone who works on tracking. Why don't the old methods work as well? I'm thinking of approaches that use, simple cosine similarity on raw features from models like DINO or DIFT.
That's a great question. And it gets to the heart of why diffusion models are so powerful here. The key difference is filtering.
Filtering.
Yes. Raw features from these models are optimized for one thing, generating an image. If you just take those raw features and measure their similarity, you get a lot of noise. A lot of dispersed, unstable results.
I'm looking at the paper's visualizations right now, and you can see it. They track a point on a camel, and with raw features, that point just explodes. It smears all over the background. It's totally polluted.
Exactly. Because the raw features are encoding way too much information that isn't relevant for just tracking one thing consistently. But self-attention. It uses learned query and key projections before it computes similarity.
So there's an extra step.
A crucial extra step. Those projections act as powerful semantic filters. They basically throw out the junk and keep only the information that's critical for the object's identity. And that gives you much cleaner, much more focused tracking.
And the numbers back that up, right? This isn't just a small improvement. On Davis 2017, the self-attention method gets nearly, double the performance of cosine similarity.
It's almost twice the performance, yeah.
Yeah.
When you measure it with JNFM, which is the standard metric.
Which, for our audience, is Jacquard and F-measure. It balances how accurate the region is with how good the boundaries are.
Right. And a jump that big just screams that the learned projections are giving you way more stability.
Okay, so that's the foundation. Learned filtered attention is better than raw feature matching. But even with this amazing emergent skill, it's not perfect right away. The paper says it's super sensitive to the noise level, the time step tau.
Yes, and this is where the really clever test time optimizations come in. Diffusion models live and die by noise. If you add too much noise, a high time step, you just wash away all the original information.
The image becomes meaningless.
Right. But if you add too little noise, the model isn't really using its main strength, its denoising objective, so the features aren't fully activated and performance drops.
You have to find that just right zone. And their solution is something called DDIM inversion. How does that help stabilize everything?
DDIM inversion is all about semantic consistency. So instead of just injecting random, chaotic Gaussian noise into the image,
you're injecting model predicted noise.
Exactly.
So it's like instead of just shaking the image randomly, you're shaking it in a way the model already understands and expects.
That is a perfect analogy. You're aligning the noisy version of the image with the model's learned semantic manifold. The result is that the features you get are way more stable across a much wider range of those time steps.
I can see the graph here. With random noise, the performance has this sharp little peak and then falls off a cliff. With DDIM inversion, the curve is much flatter and the peak is higher.
Which is exactly what you need for video. You need that stability.
Okay, that makes sense. So that's the first optimization. The next one deals with the fact that this is a text-to-image model. It needs a prompt.
Right. And your first instinct might be, okay, I'll just use the word dog, or maybe I'll use a fancy caption generator like BLP2 to describe the scene.
But that doesn't really work.
It barely helps. The paper shows you get maybe a marginal gain. Those prompts just aren't capturing the very specific context you need to fine-tune the propagation itself.
So they had to kind of teach the model how to propagate the specific mask, which is where mask-specific textual inversion comes in.
Exactly. They take a small set of learnable text tokens, we can call them theta, and they optimize them. But, and this is crucial, they're not optimizing them to get better at finding the object from a word. They're optimizing them to make the self-attention propagation kernel better.
So the goal is to make it so that if you apply the propagation kernel to the very first frame, it spits out a perfect copy of the mask you started with. You're enforcing self-consistency.
It's pure task-driven optimization. And what's really fascinating is what these learned embeddings, this theta, actually are. When you visualize them, they don't cluster anywhere near words like car or camel.
So they're not learning what the object is.
Not at all. They're not semantic labels. The researchers call them tunable knobs, which I think is a great way to put it.
So how should we think about that, like tuning a radio?
That's a great way to think about it. You know what song you want to hear, but the frequency is just a little bit off, so you're getting static. These learned tokens aren't the song. They're the tiny adjustments you make to the dial to clear up the static. They fine-tune the attention maps to get the clearest possible propagation signal.
And that little non-semantic tweak gives a huge performance boost.
A huge boost, about 3.8% in JNFM. It just proves you're optimizing the mechanism, not the content.
That is a phenomenal insight. And the last piece of this optimization puzzle is about multi-head attention.
Right, adaptive head weighting. So multi-head attention is designed to capture all sorts of different relationships. Some heads might look at texture, others at boundaries, others at the overall shape.
And for a tracking task, some of those are probably just distractions.
Exactly. Some heads might get fixated on, say, high-frequency noise in the background, which would just mess up your tracking kernel. So instead of just averaging all the heads together, which is the standard approach,
they learn weights for each head.
They learn weights for each head at each layer, and they optimize them at the same time as the textual embeddings.
Yeah.
It lets the model emphasize the heads that are actually useful for tracking and suppress the ones that are just noise.
Yeah.
And again, you see a consistent score improvement.
Okay, now let's talk about the practical side of this. We have DDIM, we have this mask-specific textual inversion, and we have head weighting. That's a lot of optimization for every single object you want to track. The paper says the textual inversion alone takes the 141 seconds per object. That's not real time.
You hit the nail on the head. That is the central limitation here. Absolutely. The inversion part, even though it's a one-time cost per object, it's a heavy one. It basically rules this out for any kind of large-scale, real-time application right now.
So it's a trade-off.
It's a fundamental trade-off. You get this incredible, unparalleled zero-shot accuracy, but you're paying for it with a big computational bill up front. Future work is going to have to tackle that overhead.
Definitely. For now, it's more of a proof of concept, a demonstration of what's possible. So let's talk about the full system, D-drift. How do all these pieces come together in the final architecture?
So the full DF system uses multi-frame label propagation to keep things stable over time. This is a pretty standard technique in tracking, but it's essential here.
How does that work? Because I imagine if you only rely on the frame right before the current one bad prediction could send the whole thing spiraling off course.
Catastrophic drift, exactly.
Yeah.
So to fight that, D-drift aggregates masks from a few different sources. It looks at the frame just before, sure, but it also looks at the initial ground truth mask, M0, and up to 7 other recent frames.
So it's constantly checking back with the original reliable mask.
Exactly. By referencing M0 and integrating a few recent guesses, it becomes much more robust to little errors and long-term drift. It's really what lets it perform so well on long videos.
So even with all that stabilization, diffusion features still aren't perfect for one thing, getting super sharp, clean boundaries. And that's where the segment anything model, or SAM, comes in.
That's right. SAM is used as a post hoc refinement step, a very powerful one. DRFT gives you a soft mask prediction, a probability map. And thanks to all the optimization work, that map is an incredibly strong, temporally consistent clue about where the object is.
So they use that probability map to guide SAM.
Yep. They sample a couple of points from that distribution. They do that 40 times, and that generates 40 candidate masks from SAM.
And how do they pick the best one out of those 40?
They just pick the one that has the highest soft IOU intersection over union with the original soft mask that DRF produced. So you're using drift's temporal consistency to guide SAM's amazing spatial precision.
And the ablation studies show this is the single biggest jump in accuracy. It takes the JNFM from about 75% all the way to over 81%.
It's a perfect partnership. DRF gives SAM such a good, reliable region to work with that SAM can just focus on what it does best, drawing a perfect outline.
So let's talk about the final results, because the performance on the benchmarks is really the punchline here.
The performance is just phenomenal. On Davis 2017, even the pure drift model, without SAM, beats other strong zero-shot methods like Dino by a really significant margin. We're talking a nearly 6% relative improvement.
So the emergent skill itself is just better.
Demonstrably better.
Oh.
And then when you add SAM, the full drift framework starts surpassing methods that were explicitly trained on huge segmentation datasets like SedGPT and even approaches that use external point trackers.
And it really shines on the hard stuff, right? The long video.
Yeah, that's where it really stands out. The long videos benchmark is designed to break trackers, to test their ability to avoid drifting over hundreds of frames.
Yeah.
A lot of methods that rely on just spatial similarity, they really suffer there. Their performance plummets.
But drift holds up.
Drift maintains really high performance because its propagation kernel is based on this deep semantic understanding, which is just more robust to drift over time. It's kind of incredible that it's more robust than some methods that were actually trained on video.
It really is remarkable that a zero-shot method, born entirely from static images, can get scores this high just by cleverly repurposing what's already inside the model.
To kind of sum it all up, the breakthrough is that these image diffusion models have this powerful emergent skill for video tracking. And we can unlock it by reinterpreting their self-attention and then stabilizing it with some smart task-specific test time tuning.
The accuracy is undeniable, even if the compute cost makes it impractical for now. But the discovery itself is what's so profound, that these foundational models have emergent temporal reasoning, and that raises a really interesting final thought for you to chew on. If these image models implicitly encode complex motion and tracking just in their self-attention maps, a mechanism designed for spatial coherence, what other complex knowledge, like maybe 3D structure or even intuitive physics, might be lying dormant in there, just waiting for the right question or the right optimization to be unlocked?